This recording is all about the review problems for Chapter 7. So, looking at number 1 on page 261. Number 1, when a solid wheel rotates about a fixed axis, do all the points on the wheel have the same tangential speed? So when you talk about a solid wheel, they're talking about something, perhaps envision a record. And they're talking about all the points, do they all have the same tangential speed? Let me draw a couple spots. Would this spot and this spot and this spot all have the same tangential speed? The answer is yes, because those spots would all have the same radius, so they would have the same tangential speed. But what the question maybe doesn't illustrate for you is that this spot here that has a shorter radius, and this spot here that has a shorter radius, and this spot here that has a shorter radius. All points in that wheel are going to be moving with the same angular speed as we discussed in class, but because the spots that have smaller radiuses are closer to the middle, their tangential speeds will be much less. Number 3, describe the path of a moving body whose acceleration is constant in magnitude, but at all times is perpendicular to the velocity. So the path of a moving body, if your acceleration is constant, but it's perpendicular, that means that you are moving in a circle. That's pretty much the definition of circular motion. Looking now at number 8, a building superintendent twirls a set of keys in a circle at the end of a cord. If the keys has a centripetal acceleration of 145 meters per square second, the cord has a length of 34 centimeters. What is the tangential speed of the keys? What you do here is you plug in that acceleration they give you, and you plug in the radius they give you. You would have to multiply both sides by the radius, giving you vt squared equals those two numbers multiplied together. Then you would square root what you have over here to find the tangential velocity. Let's now take a look at number 9. Now number 9 is also very similar. Again, they give you the acceleration of 28 meters per square second, and they give you the radius of 27 centimeters. Make sure you put that meters, and again, you'll multiply by your radius. Whoops, come back here. You'll multiply by your radius, and then you'll square root to find the tangential velocity. One thing you might want to do with a problem like this is you have to also be able to not just solve for tangential velocity, but you need to be able to solve for the centripetal acceleration alone, given the velocity and the radius, or given the acceleration and the velocity, you need to be able to solve for the radius. Now looking at number 11 here, you got Tarzan swinging on a rope. They give you the radius, they give you his tangential speed at the bottom. What they really want to know in this problem is, what mass will Tarzan have what mass will he not break the rope? And they tell you that the rope, the vine, whatever it is, can sustain 1 times 10 to the third newtons. That's 1,000. So basically, you have to find out, for 1,000 newtons of force, what mass can Tarzan be, given this equation, where centripetal force then equals mass times Vt squared over r. So you put in your 1,000 newtons, you put in your Vt, and you put in your r, solve for that, figure out what the mass is. Because when you think about it from a visualizing, if he would put 1,001 newtons on that vine, it would break. So you really want to find out what mass can he be for the vine to not break. That's what you're looking for in number 11. For number 12, now we're talking about the universal gravitational force equation. Well, gravitational force. And when you look at the equation here, gravitational force equals the universal gravitational constant times mass 1 times mass 2 over r squared. And we look at the question here. Identify the influences of mass and distance on gravitational force. Well, and the questions are like we had on these pages here, where if we double the mass, we would double our force because it's in the numerator and there's no squared going on. So doubling it or having the mass or doubling the mass will either double, if you double the mass, you'll double the force. If you take half the mass, you'll have half the force. Versus if you put that down here in the numerator with the distance, if you double your distance here, that is being squared. So if you double the distance, you're not dividing by 2, you're dividing by 4 really. Same thing if you have half the distance, you're not doing half, you're not dividing by half, you're dividing by a quarter. And so that it amplifies it, I guess is the way to really look at it. So that's something to look at when you're doing problems, and that's kind of like what we're doing on these pages here with number 12. Then I have to turn back to that page here. Whoops, too far. Number 14 is next. How does the gravitational force exerted on the Earth by the Sun compare to the force exerted on the Sun by the Earth? So you're looking at your force pair, Earth on Sun on Earth, and back and forth. Well, they're going to be equal and opposite. And you'll notice if you look into astronomy at all, the way they're finding a lot of planets nowadays, it's not that they're seeing the planets. You could have a blink of the star, but also one way they find these theoretical locations of planets is by the wobble of the star because of the force put on it by the planets. They can do some calculations to figure, oh, it's wobbling this much. There must be a planet of such and such size, because the force of the planet on the Sun is the same as the force of the Sun on the planet. Same as the force of you on the Earth is the same as the force of Earth on you. The difference is you don't really move the Earth very much because your mass is so very, very small compared to the mass of the Earth. Looking at number 18 now. Here we're doing a gravitational problem again, and they give us the force between two students. They give us the mass of both students and finding the distance between them. Let's look at that equation. So they give you the force, they give you mass and mass, find radius. So you'll have to multiply radius over, divide force over, and then you'll end up square rooting to solve for it. And same with number 19. Here they give us these two very small items, an electron and a proton. And you put in mass of the proton, mass of the electron, and the force between the two, and again, you'll solve for radius. Now, these are the two problems in there about this kind of calculation. I want you to also be able to find a mass, given a radius and the other mass, and I also want you to be able to find the force. So you have to be able to manipulate those equations in all directions. I believe 18, 19, finish off the review questions for Chapter 7.